In modern structural engineering, solver accuracy is a baseline assumption. The actual differentiator between competitive firms is data fidelity, the ability to keep information reliable as it moves from a BIM model into analysis and documentation. When a physical building model silently diverges from its mathematical counterpart, it creates massive project risk. The analyzed structure no longer matches reality. This divergence is fueled by manual data handovers. Every time an engineer re-enters coordinates or rebuilds a load profile across tools, geometry drifts and critical design assumptions are lost. These vulnerabilities are most acute during three specific transitions: moving from BIM to analytical models, transferring forces to local connection design, and translating design checks into production detailing. There is a common belief that BIM to analysis interoperability functions as a push-button solution, an automated process that executes structural design without manual intervention. This fallacy is dangerous. It assumes software can safely guess complex structural intent and load paths, effectively handing critical engineering decisions over to a generic algorithm. Using PROKON 5.3 as a blueprint, true workflow connectivity automates manual transcription. This shift focuses the engineer entirely on direct validation. Eliminating the burden of rebuilding grids and section assignments across tools redirects your attention to the structure's behavior. Software integration exists to isolate and protect your core competency. It removes administrative repetition so you can apply rigorous judgment to structural behavior. The continuous workflow begins in the architectural BIM coordination space, typically within Autodesk Revit. To bridge this space with the analytical environment, ProDesk acts as a bidirectional link between the physical Revit model and PROKON Sumo. This handshake transfers the primary structural data, physical geometry, cross-sections, and analytical centerlines. Structural idealization remains a manual requirement after transfer. Software cannot reliably dictate boundary behaviors based purely on architectural geometry. When that volumetric model strips to its analytical skeleton, intersections demand human validation. You must manually dictate if boundary conditions are sprung, fixed, or pinned. You must interrogate rigid offsets and eccentricities, and confirm diaphragm constraints, mesh connectivity, and stiffness distribution across load paths. Analytical models and physical models serve fundamentally different purposes. Engineering judgment must dictate how the mathematical model represents the real structure. The time recovered by bypassing manual model transcription is intended to be spent answering these exact behavioral questions. The BIM to FEA handshake eliminates repetitive setup, so rigorous engineering checking can begin immediately. Once the idealization is validated, PROKON Sumo acts as the central hub for the structural analysis. You can evaluate linear response, second-order effects, and buckling limits, and seismic performance within one file. Because walls and transfer plates behave differently than standard line members, Sumo utilizes finite element idealization, combining shell, plate, and solid elements with the main frame analysis. Using a unified analytical model for multiple investigations prevents the project from splintering into disconnected, out-of-sync file sets. Once the global behavior is firmly established and validated, the engineering workflow moves efficiently toward localized, code-based structural design checks. Internal forces and load vectors extracted from the global analysis feed directly into specialist environments, such as Idea Statica or PROKON's anchor bolt module. Automated data export eliminates manual transcription errors while leaving the final design execution firmly in the hands of the engineer. You must still define the detailing constraints, mechanical fastener limits, and edge distances within these modules. This phase also requires you to verify the governing standards, including the specific ASCE 7-22 parameters and combination logic for the project location. Downstream integration ensures mathematical data fidelity, but relies entirely on human judgment to define failure mechanisms and local constraints. The verified structural design intent must eventually be translated into buildable information. PROKON 5.3 addresses this through its detailing workflow tools, ProBar for CAD environments, and pads. Traditional detailing is plagued by high-volume friction, specifically manual redrafting and late-stage mismatches between the analysis and the drawings. Tools like ProBar use dynamic dimensions to combat this, ensuring annotations update cleanly as the geometry is refined. This creates a direct link between global analysis and localized detailing. When forces scale up in the analysis node, rebar diameters and dimension callouts scale to match. These toolsets support dynamic previews for bar editing, and smooth drawing modes speed up high-pressure iteration cycles. The detailing phase is historically where the design model diverges most frequently from construction reality. Connected detailing tools keep the physical reinforcement quantities perfectly aligned with the latest global analysis iterations. Software efficiency and production tools ensure structural fidelity is maintained from the analysis model directly to the construction site. This complete, continuous data loop, from BIM coordination to analysis and detailing, creates a resilient engineering environment. When a late-stage architectural change occurs, the connected network propagates the update through the structural nodes, steel connections, and drawing lines rapidly. Workflow integration guarantees more traceable steps throughout the design cycle. This traceability is proven in the final critical step of the structural workflow, reporting. In professional practice, a design calculation is entirely useless if it cannot be audited and reviewed by a third party. The editable rich text format export capability in PROKON 5.3 is specifically designed to support this administrative requirement. Engineers use these editable reports to provide narrative context, documenting structural assumptions, meshing strategies, and revision control logic. A robust, reviewer-friendly engineering report justifies governing forces through explicit logic and documented assumptions. The most effective engineering consultancies utilize connected pipelines to protect structural intent across the entire project lifespan. Modern structural software ecosystems automate data transfer, so engineers can dedicate their time to interpreting behavior and delivering safe structures.